name is Sushant, and today I will be speaking about my course project for EEL 6825, which is titled Face Recognition Using Eigenfaces, Fisherfaces, and Laplacianfaces. To begin with, I will briefly introduce the topic of face recognition and what is it that I have done in my project. Next, I will speak about the training data that I have used for this project, followed by the Eigenfaces, Fisherfaces, and the Laplacianfaces algorithm. Next, I will talk about the various distance metrics that I have used for classification. After this, I will provide a brief simulation of the three algorithms, followed by the results of my analysis, and finally the conclusion. The human face is the most common feature that is used for identifying people. As a result, face recognition has gained popularity, and several advancements have been made over the past few years in the field to develop an algorithm that can be capable of recognizing faces under various conditions such as lighting, pose, number of training samples, etc. This paper seeks to compare three such algorithms and their error rates using different distance metrics. The three algorithms that are compared are face recognition using principal component analysis, linear discriminant analysis, and locally preserving projections. The metric that is used for comparison is the distance metric, more specifically the Euclidean distance, the Manhattan distance, and the Chebyshev distance. Of all the recognition techniques, face recognition is considered to be the most ideal technique for recognition, given its unobtrusive nature, as images can be clicked using a camera without requiring the involvement or participation of the individual. Other methods, such as fingerprint recognition or iris recognition, are obtrusive in nature and require the active participation of the individual who has to place his or her finger on the fingerprint scanning device or place his or her eye on the retinal scanner. Owing to this fact, face recognition is the most preferred among all forms of biometrics. The three algorithms discussed in this project perform face recognition on contiguous lines. All these algorithms require acquiring an initial set of training images. These images are then projected into a subspace called the face space, comprising of important features of the image. The image that needs to be recognized is also projected onto this face space, and its similarity with a class is determined by using a distance metric. After the recognition task has been carried out, the three algorithms have been compared by determining the error rates for different number of training samples and for different metrics. The training set. All the images used in this paper have been taken from the AT&T database. This database comprises of a total of 400 images. That is, there are 10 images each of 40 individuals. An important feature of this database is that the images of each individual have been taken in various poses and expressions. Also, some individuals have images with and without glasses. These features make the face recognition task more challenging than usual. Every image in the database is a grayscale image and has a dimension of 112 × 92. From these 400 images, the images belonging to the first 10 individuals have been chosen. Of the 10 images per individual, 8 have been chosen for training, while the remaining 2 have been chosen for testing. Also, 5 random images of individuals whose images are not there in the training set have also been chosen for testing. In short, there are 80 training images and 25 test images. The Eigenfaces algorithm. Face recognition using eigenfaces was first introduced by Turk and Pentland and was one of the earliest techniques that was developed in this domain. This technique is based on the concept of principal component analysis, PCA, which is a very popular technique used for dimension reduction in recognition and compression algorithms. PCA is also sometimes referred to as the eigenspace projection. This method utilizes an information theory approach to highlight important local and global features in an image. PCA is a very popular method as the images are projected from high-dimensional and highly correlated image spaces to a much lower dimensional subspace where there is no sample covariance between the image features. These lower dimensional projections are called as eigenfaces. They represent a set of those features which take into account a global variation among the face images, which account for the maximum variation among the training samples. A significant drawback of this technique is that if the training set comprises of face images, taken under different elimination conditions, then some of the eigenfaces will contain information about this variation in lighting. As a result, there is a possibility that all the points in the phase space might not be well clustered. The second algorithm that has been used is the Fisherfaces algorithm. Fisherfaces is yet another technique widely used in face recognition procedures. This technique is a derivative of R. A. Fisher's linear discriminant idea, which he proposed in 1936, and is considered as a classical technique in pattern recognition. Fisherfaces arise when linear discriminant analysis is used to convert the training image samples into basis vectors. An important assumption of this method is that the data is uniformly distributed in each class. Since the training set is already labeled, this information is utilized in reducing the dimensionality of the features. FLD is an example of a class-specific method, as it attempts to shape the scatter of the points in order to have a more reliable classification. The eigenvector matrix is then selected in such a way that the ratio of the between-class scatter and the within-class scatter is maximized. An important reason why LDA is preferred over PCA is because PCA has a tendency to group the classes in the projected phase space in such a manner that it cannot be linearly separable. Although it achieves a greater scatter, LDA is capable of achieving a better between-class scatter, which only improves the classification process. The main advantage of the Fisherfaces algorithm over the Eigenfaces algorithm is that it is capable of providing a high recognition rate even if the face images have been captured under varying elimination conditions. Besides this, it is faster and can handle images with different poses and facial expressions more effectively. Finally, the third algorithm that has been used is the Laplacianfaces algorithm. When PCA and LDA are used for face recognition, only the global structure is preserved. But in some applications, preserving the local structure is also desired. For such cases, another algorithm called the locally preserved projections (LPP) is utilized. The aim of this algorithm is to learn a locally preserved subspace with the aim of preserving geometry of the data along with the local structure. When the face images are projected into a lower dimension phase space using this algorithm, the images that are obtained are called as the Laplacian faces. They are the optimal linear approximations to the eigenfunctions of the Laplace-Beltrami operator on the face manifold. Also, the Laplacian faces have been known to eliminate or reduce unwanted variations that arise due to varying eliminations, pose, or different facial expressions. The LPP algorithm is the only algorithm that explicitly considers the face manifold. The advantage of using LPP is that it is capable of detecting a nonlinear manifold structure. The PCA and the LDA algorithms model the faces only in the Euclidean space, and hence they see only the Euclidean structure. These conventional algorithms fail to detect the intrinsic low dimensionality. Moving on to the distance metrics. The distance classifiers are the last component of most face recognition algorithms, which is used for classifying the test image into a particular class. It is of importance as it provides vital information regarding the similarity of two images. This similarity is determined by applying the distance metric to the test image vector and every training image vector. The three distances that have been explored in this paper are the Euclidean distance, the Manhattan distance, and the Chebyshev distance. All these distances have been described. The Euclidean distance. The Euclidean distance is the most commonly used distance metric for face classification in most face recognition algorithms. It examines the square root of the square difference between the test image weights vector and the weight vector of an image in the training set. It is also sometimes referred to as the L2 norm. The Manhattan distance. The Manhattan distance or the city block distance, commonly referred to as the rectilinear distance or the L1 norm, is another distance metric used for face classification. It examines the absolute differences between the coordinates of the two weight vectors. Finally, the Chebyshev distance. The Chebyshev distance is also called the maximum value distance and is defined as the greatest of the differences between the two vectors along any dimension. It is also sometimes referred to as the L infinity norm. Now, I will be presenting a simulation of the three algorithms. All the three algorithms have been written using MATLAB. Now, this is the code for the Eigenfaces algorithm. As you can see, the code has been well commented, which makes it easy to understand. The first window displays all the training images that are present in the dataset. The second window displays the mean image, while the third window displays all the eigenfaces that are generated. The program now requires us to enter the name of the image that needs to be recognized. Say I enter test4.pgm. As you can see, Figure 4 represents the input image and the weights. Figure 5 displays the input image and the image that it has matched using the Euclidean distance metric. Figure 6 displays the input image and the image that it has matched using the Manhattan distance, while Figure 7 displays the input image and the image that it has matched using the Chebyshev distance. Moving on to the Fisherfaces algorithm. Now, this is the Fisherfaces algorithm. Again, you can see that the code has been well commented, making it easy to understand and implement. Again, the first window displays all the training images that are present in the dataset. The second window displays the mean image. The third window, as you could see, displays the average image of each class, while the fourth window displays all the Fisherfaces that are generated. Again, the program requires us to enter the name of the image that needs to be recognized. Say I enter test6.pgm. As you can see, the fifth window displays the input image and the weights. The sixth window displays the input image and the image matched using the Euclidean distance. The seventh window displays the input image and the image matched using the Manhattan distance, while the eighth window displays the input image and the image that is matched using the Chebyshev distance. In case the test image belongs to a person whose image is not present in the database, then a message saying the person does not belong to the database is displayed in the command window. Now finally, the third algorithm, which is face recognition using the Laplacianfaces algorithm. This is the program. Again, you can see that the code has been well commented, making it easy to understand and implement. The first window, as usual, displays all the images that are present on the training set. The second window, as you could see, displayed the mean image, while the third window displays all the Laplacian faces that are generated. Again, the program requires me to enter the name of a test image that I would want to be classified, so I enter test10.pgm. As you can see, again, the fourth window displays the input image along with its weights. The fifth image displays the input image along with the image that it has matched using the Euclidean distance metric. The sixth window displays the input image along with the matched image using the Manhattan distance. And finally, the seventh window shows the input image along with the matched image using the Chebyshev distance. Moving on to the results. The three algorithms were compared by calculating the error rates for different number of training samples. Apart from this, the error rates for each algorithm for different distance metrics were also determined. Also, the average runtime for each algorithm using different distance metrics was determined. The average runtime of the algorithms was determined by running the first 10 test images. All the results have been tabulated as shown. It can be seen that the Fisherfaces algorithm using the Manhattan distance metric ran the quickest. Also, the Manhattan and the Chebyshev distance metrics are comparatively faster than the Euclidean distance metric, owing to a lesser number of computations that are required. The variation in the error rates with the number of training samples that were determined for the three algorithms have been described in the following figures. Figure 1 shows the variation of the error rate for the three algorithms using the Euclidean distance metric. Figure 2 shows the variation of the error rate for the three algorithms using the Manhattan distance metric, while the third figure shows the variation of the error rate for the three algorithms using the Chebyshev distance. Figure 4 shows the error rates for the Eigenfaces algorithm using the three different distance metrics. The fifth figure shows the variation in the error rates for the Fisherfaces algorithm using the three different distance metrics, while the last figure shows the variation in the error rates for the Laplacianfaces algorithm using the three different distance metrics. An important point to be noted here is that all the training and the test images were resized to half their original size before being fed to the Fisherfaces algorithm, owing to the large number of computations that were involved in calculating the within class and the between class scatter matrices. Finally, moving on to the conclusion, the least runtime observed was that of 4.77 seconds for the Fisherfaces algorithm using the Manhattan distance. The least error rate that was achieved was that of 4% for the Fisherfaces algorithm with the Chebyshev distance metric. Besides this, some other results that were observed was that of the Chebyshev distance metric was the best distance metric when it came to recognizing images that were not a part of the training database. The other distance metrics were unable to classify images not belonging to the dataset as effectively as the Chebyshev distance. Given a few exceptions, the error rates for all the three algorithms decreased with an increase in the number of training samples. In case of Eigenfaces and the Fisherfaces algorithm, the Manhattan distance metric either matched or outperformed the Euclidean distance metric for all sizes of the training dataset. For all the algorithms, the threshold values were determined by calculating the minimum distance for each test image for a training set comprising of 80 images, and then setting the values heuristically that would yield the least error rate as possible. Well, this was my project. Thank you for watching.